Welcome to AP Podcast 13.4, 13.5. What we're going to be talking about today is heterogeneous equilibria and applying the constant K to some equilibrium problems. So heterogeneous equilibria is when you have an equilibrium that's more than one phase. So for example, imagine that we have our standard reaction of A plus B yields C plus D, right? And here we have an AQ, and we have a solid, and then we have AQ and AQ, okay? When you have different phases there, that's the heterogeneous equilibrium. And it turns out when chemists run experiments, they've found out that the solids and pure liquids, that's another thing, solids or pure liquids, like for example when we just have water, right, and you see it as an L, that those are not part of the equilibrium expression. They don't affect K. And basically the idea is that the concentrations of the solids or the pure liquids aren't really changing. If you have water, you have 55 moles per liter, and that's not going to change no matter how much more water you add. So since those don't change, we do not include them in the equilibrium expression. So let me just show you an example of that. So here we have iodine in the solid state up here. Okay, we have the iodine in the solid state, and then we have hydrogen in the gas state and HI in the gas state. All right. Now normally we would write the expression out like this: products, right, over the reactants. However, since iodine is in the solid state, and that concentration is not going to change, the equilibrium is going to be based on the concentrations of the HI and the H2. And so that's really as deep as we have to go. It's not too bad. So let's go ahead and take a moment and practice a couple. Pause the video, see what you get. All right, this is how I would approach this first one. I would do products over the reactants. So K equals, and I would put the concentration of CO, because it's in a gas. And then notice this: water's in the liquid state. It's not part of the expression. And then over CO2 and H2. So there you have it. All right. Again, we're leaving out the solid state. Now, if we were doing the next one, look at this. We've got a solid on that reactant and a solid in that product. So the K for that reaction is simply CO2 squared over CO squared. And so there you have it. Pretty straightforward, right? So that's heterogeneous equilibrium. So this leads us to applying the equilibrium constant. And I got to tell you right now that this is where it starts to get a little tough for students to understand. So you just kind of got to bear with me. We're going to do a lot of practice problems in class to get this down. But here are some fundamental things that we have to be aware of. Okay, when you have a reaction that has a lot of K, and remember, to find K, it's products over the reactants, right? If you have a lot of K, that means essentially the reaction has gone to completion. So if I think about, here are my reactants, here are my products, right? If K is big, that means this number up here is large, right? And this number down here is small. Hopefully that makes sense to you. So that tells us that there's a lot of products being formed and very few reactants. So if you get a big K, and it's kind of hard to say what it is, but I would say anything over 100 we would consider a large K, and some people might consider that even too big, but that's something, if you see that, you know it essentially goes forward. Now the opposite, if you have a very small K, and we're going to be dealing with a very small K quite a bit. So on a very small K, what we would get there is our reactant, oops, way up here, our product value would be small, and our reactant value would be large. And so, I mean, let's just put some numbers in. Let's just say maybe we got a value of 5 right there, and maybe up here we had a value of 150. Okay, so if you get a situation like that, that's a small K. And so that tells us that the reaction doesn't really go forward very much, because the amount of reactants is still very large compared to the products. So you can kind of get a feel for how much the reaction goes just basically by looking at K. Now this other thing, look at this. Time to reach equilibrium. All right, you see that right there? Time. Now when you think of time, hopefully you think about kinetics, right? How fast the reaction goes. And the thing we want to remember is that K does not tell us it's going to go fast. Remember, that's going to really depend upon the rate, which is kinetics, and the activation energy to get there. So here's the next big thing. This is the reaction quotient. And what this does is oftentimes you will be, well, not oftentimes, but some of the times you'll be given some initial concentrations. And the question will say something like this. Will this reaction proceed forward to the product side, or will it stay more towards the reactant side? And so what we're going to do is we're going to take those values that they give us and we're going to look at what happens to the numbers. And then if we can compare that to the K, we can figure out what's going on. Now there's some really nice things about figuring out Q. The beauty of Q is, look at this. It's still products over the reactants. So mathematically, you do not have to do anything. The important thing is that you understand that when you're calculating Q, your system is not at equilibrium. All right? We're dealing with a situation where we haven't reached equilibrium yet, and we want to compare it to what we know is the K for the system. And so we'll be given a K. So now, how does that relate? What happens when K is bigger than Q, and so on and so on? Well, here's some general stuff, and you definitely want to get this down. All right, and I'll show you the Richardson way, the way I remember this. So if Q is less than K, that tells us there's not enough products, and so you get a shift to the right. So again, this is kind of how I visualize it. I just basically think of what is K? K equals the products over the reactants, right? And so if Q is not as big, so let's say K, we get a value of 10, right? Now when I calculate Q, let's say I get a value of 1. Well, if I get a value of 1, how does that going to go to 10, right? Just to make this simple, let's say the products is 10 and the reactants is 1. If I have a value of 1 and it's just 1 over 1, what would have to happen mathematically to get Q to go to K? Well, I would have to make more products, right? I would have to make more products. So this number right here would have to increase. And that tells me that we're going to be forming more products. So initially we get a Q value of 1, but we've got to get to 10. The only way that could work is if we form more products. The opposite would be true if Q was larger. Let's say, for example, that Q in this case is now 10, right? I'll go 10 over 1. And that K equals 1, right? Well, in order for if we know K has got a value of 1, what has to happen to Q in order to get there? Well, you've got to make more reactants, right? So the value down here has to increase. All right, I've got a lot of arrows. I hope this is making sense. But mathematically, sometimes it's really easy to think about it that way. So if Q is larger, then we've got to form more reactants. The product value's got to go down, and then we've got a situation where we're forming more reactants. Okay, and then if you have a situation where Q and K are equal, well, then you're at equilibrium. All right. Now here's another way I think about this, and if a professor of chemistry saw this, I don't know if they'd laugh at me or whatever, but I tell you what, it keeps it in my brain. I like to think of Q being on this side, so I look at it this way. Let's imagine exactly what we have up here with Q and K. All right. Now, let's say I've got a value of 10, like I said before, and a value of 1, right? Q gives 1 and K equals 10. K is bigger than Q, right? Q is smaller. So the reaction has to shift right. We got to go towards the bigger thing. And look what it says right there. Hey, if Q is small, you shift to the right. What about if it's the other way? What if Q is 10 and K is 1? Well, I've got to shift towards the bigger number. which means shifting left. And then look what it says right there, shift left. So you guys have known me for years doing this kind of stuff, trying to make it easier in my mind, and that's how it works for me. When I'm calculating Q or K, I shift to the bigger one, and that tells me what's going to happen. So I hope that makes sense, and if I just did a terrible job of butchering this, we'll get it straightened out in class. So there's the Richardson way, and hopefully that'll make sense. Now let's try and use this reaction quotient so you can see what I'm talking about. So there's our reaction, and look, they give us K. And let's notice the magnitude of K. Okay, really small, right? Something to the negative fifth power. So we've got an experiment, and you've got 0.1 molar of this guy right here. So I've got 0.1 mole. And for the NO, I've got 0.0010 moles. And on this one, I've got 0.00010 moles. So I'm running out of room there. Okay? So they're mixed in a 2-liter flask. Which direction will the reaction proceed to reach equilibrium? So in this situation, we've got to calculate Q. Alright, so let's figure this out. Now, notice right here, we've got ourselves a 1-liter flask. Okay? This is important that you pay attention to that. 1-liter flask and the number of moles makes it nice and easy. But every once in a while, they'll put a half a liter, 2 liters, 3 liters, and we've got to prepare for that, because what they'll do is we'll have to calculate a molarity. But we're going to make this one easy right now and not really worry about it. So let me give myself some room here, and let's figure this out. So if I was writing this out, I would go Q equals, right? And I would do 0.001 squared over 0 times 0.0001. And I didn't write out the equilibrium expression. Hopefully you guys can handle that. Divided by 0.0, oops, pardon me, just 0. Let me just do this, 0.1 squared, right? Now when I work that out, I get a value of 1 times 10 to the negative 8th. Okay, so again, I think this way. Rather than memorizing what's got to go bigger, I write it like this, and look what K is. 1.55 times 10 to the minus 5th, and here's Q right here. Okay, Q is smaller than K. So again, if we think of K being the products over the reactants, and the only way for us to reach this equilibrium is for the number to get bigger, right? R's got to go down, right? Or you could think of the value of the products has got to go up. So what that tells us is this reaction's going to shift that way. It's going to shift to the right. All right, so that's how we use the reaction quotient. This reaction would, up here, what we would get is we would get a shifting this way. We'd make more products and less reactants, and to reach equilibrium. So there you go. Hopefully that makes a little sense. We'll definitely go over this stuff in class, and I will see you guys next time.